I wanted to show you an example of a longitudinal standing wave. On the last problem, we looked at a wave on a string, and that was a transverse wave, right? Where the wave was propagating left and right, but the elements of the medium, parts of the string, were oscillating up and down. Now we see a longitudinal wave, and I'm going to zoom in just a second so you can see better. But maybe let me pause this for a second. So I have a spring here, right? And I just wanted to show you, I believe I set this up. This is a 20 gram. This is a 50 gram. I don't know what the error tolerance is, less than a gram. But I want to point out something before we get too crazy here. Let me move this out of the way. There's a big magnet in there. It is a speaker. This is only approximate, but I hope you could see that at the location, when this spring is connected to the oscillator, it's stretched the same as if 70 grams was hanging on it. So we could convert that 70 grams to kilograms and multiply by G and figure out the tension in the spring. So I just wanted to point out basically 70 grams times G, when you fix up all the units, etc., is the tension when this thing is set up like this. Is that about right? It's pretty close. So we do know the string tension. Now, I don't want to be perfect here, but whatever. Let's just say that's about 74, 75 centimeters, depending where we want to start and stop the end of the spring. Like, do we have to count the hook or not? Whatever. So let's just say it's about, this is a meter stick, so that's about 74 centimeters. And now, when I run this thing, let's give it a second to reach equilibrium. I'm going to zoom in the camera here. Let me check what the camera looks like. So you're seeing the whole thing right there. And give me just a second to zoom in, but I do want to point out there's a region here where the spring is not moving and a region where it is. Not moving, it is. Not moving, and it is. So you could guess those are nodes and antinodes. If I zoom in a little bit, you might be able to see it better. Give me a second. I want to get the bottom there. And you can see the oscillator. In this case, the oscillator is moving very rapidly up and down, but on your screen, it looks like it's moving kind of slowly. And that's because this is moving 27 times per second, as dictated by this number here. Is it 27? About 27 hertz, right? And because the camera rate is 50 or 60 or something like that, there's a little bit of aliasing. And so it's kind of like a strobe effect, and that's kind of cool. But now, before we go to the board, I want you to think about this. Maybe you can see that in this longitudinal wave, now this oscillator here, this is a maximum of displacement, minimum, maximum, minimum, etc. In our phrases, you could say this is an antinode now. This is a node, antinode, and node. And I'm going to see if you can see that at all on the screen. It's kind of hard to see, but the regions where the spring is most blurry are antinodes, and the regions where it's not. And I can tell you here, maybe if I zoom out just a little bit, we could try and see if we can count those nodes and scroll up. Let me go out just a little bit. All right. So just in case your video is kind of not that great, I see a node. So there's one node, two nodes, three nodes, four nodes, five nodes, six nodes. The very top is a node. Right here where it's connected to this rod is not displacing. So for this longitudinal wave, this becomes a node, and down here becomes an antinode. All right, so our goal is to figure out the wave speed in this spring. Okay, let's go take a look at the board now. And maybe I'll turn this to sine wave, so it's not so annoying. All right. All right, and where's my markers? All right, so our questions okay, so here is the data that I found. I massed this spring, it was 11.65 grams. We saw that the tension is equivalent to mg, where m was the 70 grams that I was hanging off of it. So if we assume that tension over mu, tension per unit mu per tension over mass per unit length should give you the wave speed, I found 7.67. Now you might think for a second, how did I get mu? How did I get mu to do this calculation? Okay, I'm going to tell you in 3, 2, 1. Mu is mass of the spring all over the length, capital L. Now we should probably be careful here. You might want to use different units for this. Now, I know from the last problem, the grams are going to end up canceling if I use grams here and grams there. But notice if I want to get meters per second for a wave speed, G has a meters per second squared in it. So I'd better use L with meters in it. Otherwise, I don't get meters squared over second squared, square rooted. So if you're wondering how I got this number, that's how I did it, but I had to use L in units of meters. Okay, so check your units. You can pause the video and make sure you get that. All right, moving on. This is supposed to be a sketch of what we saw. There was a region of the spring that wasn't blurry, that was blurry. Wasn't blurry, blurry, and I believe we had this pattern. I counted it out before I started the video. So now what I want to do is label the nodes and antinodes. Okay, nodes and antinodes. If you want to pause the video, go for it. Here I go. This is a node, antinode, node, antinode, etc. The blurry positions were antinodes. They were moving the maximum amount. The regions on the spring that were not moving at all were the nodes, minimum displacement. And now, because it's a longitudinal wave, this part we saw was a displacement antinode. Now, in this case, think, do we have mixed boundary conditions where we have n lambda over 4s equals the string length, and we can only use odd integers, or do we have matched boundaries? If you want to pause the video, great. Here it is. 1, 2, 3, go. We have mixed boundary conditions. This is the condition that we have, right? Notice one boundary is a node, the other boundary is an antinode. So we do not have matched boundary conditions. So two main differences there. We see you have to use lambda over 4, and you can only use odd integers. Think, if you used an even number, 2 lambda over 4s would be a lambda over 2. That would be an example that matches matched boundary conditions. So that doesn't make sense. You can only use the odd harmonics. Okay. So now let's see, we found, I think the frequency was 27, wasn't it? Not 26. You must have drifted a little since when I first started. That's fine. We'll use 27 hertz. And then, oh, whoops. Gee, I wonder which harmonic it is. How can I tell this is the 11th harmonic? Well, let's count. The distance between an adjacent node and an antinode, this distance right here, is a lambda over 4. So let's count the lambda over 4s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I see that in this case, our harmonic number, our integer, n, is 11. So let's try to figure out our experimental wave speed and see if it's roughly in good agreement. There's a lot of slop in this, and that function generator, you could see I was getting the same pattern whether I used 26 or 27, probably even 28. So there's a little bit of slop in there. One part out of that is like 3% alone. Anyways, let's keep rocking here. So V experimental should equal F11 times lambda 11. All right. Well, maybe let's do this more generally. We'll put in the integer at the very end. I think that's probably a better habit to get into. Derive the general result in case you need to do multiple in a lab setting. Okay, so in this case, let's rearrange this equation for lambda. It'll be 4L over N. All right. And so in this case, let's plug in our numbers here. So for N equals 11, we found 27 hertz. We know that N was 11. And then if we want to get meters per second, we'd better use the green version in meters. I think I'm forgetting something. Oh, the 4. Sorry. There we go. So let's punch all this in and see what we get. 27 times 4 times 0.74 divide by 11. I got 7.27. All right. About but clearly we're off in the second digit here, so I'm getting about 7.3 versus that. 3 out of 70, what is that? That's about 3 out of 60, which is about what? 1 out of 30 is about 3%. So this is in the right ballpark, assuming we're off probably by about 3-4% in this number. Right? 1 out of 25 would be 4%. 1 out of 33 would be 3%. This is in the kind of the region, or sorry, this is about what we expect. We might be off by a few percent, and that's what we see. So that's kind of interesting. Let's leave it at that. That's an example of a longitudinal